Okay, so chapter 2, we have seen the notes. We have gone through the lecture last sections on a Sunday. So today we'll go through the notes again quickly to see what is the thing that is missing in your notes. Okay, that the things that I wanted to write down as an additional info, and also it is something that you must know. So first, introductions. Capacitor, well, again, is a device of a store electric charge. And then the capacitor, it varies in shape, in the size. So you have a different shape, different size. Okay, but then the most important thing is that you have two parallel plates or two conductor. Okay, that is carrying equal but opposite amounts of charge. So capacitor may have important applications in electronic, and the most common capacitor is storing electric potential energy. And where does it store the energy? It's stored in the electric field in between two plates. Okay, in between two plates or two conductor. So in general, capacitor consists of two conductor plates of any shape, okay, that placed near one another without touching. So the key point, without touching. So usually there's an air gap between them. If no air gap, means that you place a dielectric between them. So all these, they are the examples of the capacitor, different shape, parallel plates you have, and then the roll up parallel plates, cylindrical capacitor, and the last one is a spherical capacitor. Okay, there are many other shapes out there, but I'm just showing you a few basic types of capacitor here. So capacitance and capacitors in a series and parallel, we've seen it before, obviously. Okay, we have learned how to derive it. So for a given capacitor, it is found that the amount of charge in each plate is proportional to the magnitude of potential difference. So this is what I told you previously. Q is proportional to V, and V is proportional to Q. So if you change that, if you increase the potential difference, charge will increase. If you have more charge stored in the plate, then the potential difference will increase. And both of these quantity, they won't affect C. Okay, they won't affect your C. So capacitance C is just a constant value. Okay, so it does not in general, now if you look at the statement, it does not in general depends, okay, it does not in general depends on Q or V, meaning that if you change V or Q, usually you won't change the capacitance unless, okay, unless if you change the physical structure of the capacitor, then because of the modifications of the shape or the physical structure, then you can change the V. And in that sense, in that case, the V will also affect your C. All right. But in general, Q and V, it won't affect your C unless you change the physical structure. So C, it depends only on the size, the shape, and then the positions of the plates. Okay, the two positions, the relative positions of two plates. And the last one is the dielectric, the material that separate them. Okay, it could be air or it could be any other dielectric material. So in short, okay, how do we know that whether C changes or not? It depends on this equation. So C equals to epsilon A over D. Now, when you talk about size and shape, you're looking at the area. Okay, you're looking at the area. When you talk about relative positions of two plates, then you're talking about the D. And if you're looking at the dielectric, then you're looking at the epsilon. Okay, epsilon is a permittivity value. It depends on the types of the dielectric. So air and dielectric, they also have different value. Okay, and then the permittivity for air can be found in the list of a constant, but from a dielectric, usually it will be mentioned in the questions. So the capacitance of a capacitor is defined as just a ratio of the magnitude of the charge on each plate, on either plate, on one plate, to the magnitude of the potential difference between two plates. Okay, which means, okay, if you look at this statement, you are looking at the potential difference across the plate, not from the power supply. So don't get confused. In every circuit, there are two potential differences. One is coming from the source and another one is across the plate, is in the capacitor. Okay, it's coming from the capacitor. SI units of capacitance is either farad or coulombs per volt. 1 farad is defined as the charge of 1 coulomb stored on each conducting plate as a result of the potential difference of 1 volt between two plates. So all this, we have seen it before. Okay, I'll go through it quickly. So we have learned how to derive it. The important things that you have to know is when you have capacitor in series, charge is constant. When you have capacitance in parallel, voltage is constant. Okay, the potential difference is constant. And then you have equations 1 over C effective equals to 1 over C1 plus 1 over C2 for capacitor in series. And then C equals to C1 plus C2 for capacitor in parallel. Now for these two equations, you have to be careful, okay, because it's the opposite to the one in a resistor. For resistor, okay, resistor, now I'm just going to mention it a bit. For R in series, we calculate R effective by adding up R1 and R2. Whereas for R in parallel, okay, we use R effective equals to 1 over R1 plus 1 over R2. Okay, so that is the difference between capacitor and resistor. So you have to know which one to use in your questions. Don't get confused, don't get mixed up. Okay, jangan keliru. Ini memang sentiasa berlaku dalam exam. Pelajar keliru. Yang mana satu yang sepatutnya guna. Okay, so capacitor dengan resistor dia terbalik. Alright, equations dia terbalik. So this one I will explain it again in chapter 3. So for now, I just want you to take note to know which equations to use in a series, which one to use in a parallel circuit. Okay, now this is the things that we want to discuss today. Examples. Okay, now this is examples questions. Determines the equivalent capacitance. So equivalent means that it's an equal value. Okay, the value that is equal. If you want to remove all this one, you want to replace with a new one. So that one we call equivalent capacitance. So all the capacitors, they are identical. Now, what does it mean by identical? Identical means they have the same shape, they are made of the same materials, they have the same capacitance and so on. Everything is the same. They look alike. That is the meanings of identical. So you have 7 capacitors right here, and they are all identical, and each has capacitance of 1 microfarad. So now you want to determine equivalent capacitance. Now, what does it mean? If you want to remove all 7 capacitors and you want to replace with just 1, all right? You want to replace with just 1. So this one capacitor, we call it C equivalent or C effective. So it has 2 names, depends on the book that you are looking at. So both of them, they mean the same thing, okay? C equivalent, equivalent capacitance, or C effective, effective capacitance. So they all refer to the same thing. It means that if you want to remove all 7 capacitors and you want to use the one that has the same magnitude as the sum of the 7 capacitor, then what is the values of this capacitor, the new capacitor that you're going to use? So that is the equivalent capacitance. So first of all, how are we going to solve a circuit? Now you have a quite complicated circuit, okay, with a 7 capacitor, and the arrangement is given as shown in the figure. So before you solve it, the first thing that I like my students to do, I always encourage my students to do, is to label the diagram. So you have 7 capacitors, you label them with a subscript. So capacitor 1, you call it C1, capacitor 2, C2, C3, C4, C5, C6, C7. You give it a name. Why? So if you label your diagram and you use a symbol in your calculations, so when you recheck your answer, you can identify where is the mistake easily. But if you didn't use any symbol, you didn't label it, you didn't give it a name, you just use the value in your calculation, it is quite impossible for you to detect the mistake. Where is the mistake? All right. So I always encourage my students to write down the subscript, to label it first, and then mention all this label, use all this symbol in your equations before you do your substitution. This is a good habit, okay, because you need to check your answer in exam. Without all this labeling, you wouldn't be able to notice, you wouldn't be able to tell where is the mistake. Okay, so kita label adalah untuk memudahkan kita cari di manakah kesilapan kita. Right? Bukan untuk dia nampak cantik ke atau apa. Untuk kita senang apabila kita semak jawapan kita. So bila kita dapati ada mistake dalam kita punya pengiraan, kita cuma perlu rujuk kepada dia punya label, dan anda akan tahu mana yang salah. Okay, or sometimes maybe you check the label and the values given, you will find that okay, you have made some careless mistake. So C1 given, for example, in this question is 1 microfarad, but in your substitution you label as 2. So when you recheck it, you see, oh, questions give me 1 microfarad and I write 2 in my solutions, then you know where is the mistake. Okay, but if you just write 2 in a solution, then when you check the answer, it is almost impossible for you to tell that 2, the values 2 is wrong because you don't know where does it come from. Okay, you only know that you use 2 because your first impression asks you to do so. So you cannot recheck. You don't know where does it come from. All right. So label it. Okay, memang label sangat penting. Tapi benda ini paling tidak disukai oleh pelajar. Saya pun tak tahu kenapa. Alright, tapi nasihat saya label. Alright, now let's see how to solve it. To calculate the effective capacitance, it is easier to solve it from the end of the circuit to the terminal. So first of all, you need to know where is the terminal. Terminal, usually it refers to the place where you connect it to the battery. Okay, where it is being connected to the battery. When it comes to a circuit, if you cannot see any battery in the circuit, then you try to identify the dot. Okay, this 2 dot, it represents terminal. So now you have a terminal on the right-hand side, according to the questions, the diagram given. The terminal is on the right-hand side. So we start from the part that is furthest away from the circuit. Paling jauh dari litar kita. Okay, in which now we have the place that is furthest away from the terminal is my C2. So I'm going to start from C2 because it is being located. It is located at a place that is furthest away from the terminal. Paling jauh sekali dah. Alright. Now, once I know I have to start from C2, what should I do next? You try to identify the junction. Okay, you try to identify the junction. Junction means that the place where you connect a different wire, different cable together. All right. So for example, now you have a C2 right here. The closest junction to C2 is this 2 point. Okay, is this 2 point. Before you join it to C1 and C3. So these are the junctions that belong to C2. So first of all, you try to see how many paths can be taken to travel from from one terminal to the other. Let's say from point A to B. Okay, ada berapa cara, berapa laluan yang kita boleh guna untuk bergerak dari A ke B. So obviously, if you look at this diagram, you have only one path, okay, which is a linear path, straight away from A to B. That is the only path that you have in this diagram. So if you look at this path, now you try to think, okay, is there more than one capacitor along the same path? There's this one path, this blue color line. If no, then that's it. If you have more than one capacitor, then you need to simplify it. Okay, if you have more than one capacitor, then you need to simplify it. But now if you look at the diagram, along this blue color path, I have only one capacitor. Therefore, I don't need to do anything. Okay, it means that I'm done with these 2 junctions, the junctions A and B, done. Okay, nothing else for me to do. So the next things that I'm going to do, okay, because the first junction is pretty useless, so I don't want it. Now I'm going to identify where is the next junction. Okay, the next junction that is closest to my C2. The 2 dots just now, they are not suitable. You don't need to do anything because they are in the simplest form already. Next, I'm going to search for the next 2 junction that is closest to my C2, which is this 2 point. Okay, this is the junction, the next closest junctions to my C2. So once I've identified the junctions, okay, I have determined which junctions to use. Okay, I need to identify now how many paths can be taken to travel from. Let's say now I'm going to call it X and Y. How many way how many path, how many laluan lah kita kata, that I can use to travel from X to Y. So first one is, okay, you have the first choice. First choice to travel from X to Y is through this long path. Okay, this C shape, inverted C shape. So if you choose this orange color path, then it will travel through 3 capacitors, right? And then the second path that we have here is this linear path. Okay, is this linear path. If I want to travel from X to Y, now can I travel from C5, C6, C7? Cannot. If you say you can travel from X to Y through C5, C7, C6, then you are ignoring these 2 cables. You are ignoring the existence of these two cables. Cannot. Okay, you cannot disconnect it from the terminal. So you cannot choose C5, C7, C6. You can only solve it from the left-hand side. Okay, tak boleh tiba-tiba switch ke kanan and then kamu kata, oh boleh juga saya pilih path ini. No, cannot. Alright, because this path, if you choose it like this, you choose a C shape like this, means that you're disconnecting this circuit from the terminal. Okay, dia sambung dengan terminal. Kamu tak boleh tiba-tiba potong dia. Okay, potong dia dengan terminal. Cannot. Alright. So meaning that now I have two choices that I can use to travel from X to Y. Okay, to travel from X to Y. So the first one is the orange path. Now, if you look at orange path, I have more than one capacitor. When I have more than one capacitor, then I need to simplify it. How to simplify it? You look at the relationship between these three capacitors. C1, C2, C3. C1, C2, C3, you look at the way they are being arranged. Obviously, they are being arranged in a series, okay, in the series form. How do I know that they are in a series form? Well, because you look at both legs from C2. One leg is being connected to C1, one leg is being connected to C3. So it is series. Parallel only exists if both legs from C2, they are being connected to the both legs of C1, for example. Then we say they are parallel. But now what you have right here, C2, one leg is being connected to C1, another leg is being connected to C3. So this is a series circuit. All right, so that's why you look at the diagram right here. I circle it, I call it series circuit. I tell you that it is a series circuit. So C1, C2, C3, they are being connected in series. And now, if I want to simplify it, I need to give it a new name. Okay, I want to simplify it, I need to give it a new name. So I call it CX. As long as you haven't reached the final step, you don't label it as C effective, you don't label it as a C equivalent. All right, even though we know that this CX is the C effective for C1, C2, C3, but because we hasn't reached final step, therefore we don't want to call it C effective or C equivalent. All right, we keep that particular name for your final answer. Therefore, you need to create a new name for it. So in this case, in my example, I called it CX. So I simplified it. I calculate the values of CX by using series equation. So when you have capacitor being connected in series, okay, you calculate by using 1 over C1 plus 1 over C2 plus 1 over C3, which is equals to your 1 over CX. So from here, you determine the values of CX. Okay, kamu kira CX dengan equation sini. Next, okay, after I simplify it, C1, C2, C3 no longer exists. What I have right now in my new circuit is CX. Meaning that now I throw C1, C2, C3 away, I replace with CX. Okay, and this CX, it has the same value as the total of the three capacitors just now. Right? So now I have CX right here. Okay, so CX, that is from our orange path. Okay, it is from our orange path. So now my orange color path, I have only one capacitor. I cannot do anything anymore. So I look at the green color path. Green color path, I also have only one capacitor. So I don't need to simplify it also. Right? I can just leave it like original circuit. Okay, leave it as it is. But now what am I going to do? I want to combine these two paths. After you simplify the path, okay, each individual path, now you want to combine the path. How to combine them? If you look at this diagram, now both legs from my CX, they are being connected to C4. Okay, left, yeah, this is left. Left leg of CX is being connected to C4, and then right legs of CX is also being connected to C4. So in this case, I know both of them, they are being connected in parallel. Okay, and now I want to simplify it, so I need to give it another new name. And in my example, now I call it CY. So I calculate CY by using parallel equation. So CY is equals to CX plus C4. Because CX and C4, they are parallel now. Okay, they are parallel now. So next step, after I simplify Cx and C4, Cx and C4, they no longer exist. Okay, what I have right now, I have just Cy in my circuit. Okay, I have just Cy in my circuit. So if you look at Cy, now these two orange color junctions, they are no longer useful. Okay, they are no longer useful in the next step. So what am I going to do? I'm going to identify next junction in my circuit. Okay, next junction that is closest to my Cy. Obviously, it's this 2 point right now. Okay, it's this 2 point right now. So I have a point A and point B right here. So the next two junctions that I'm going to use is point A and point B. So again, I'm just going to repeat the same thing. I want to identify how many paths can be taken to travel from A to B. So first one is to travel through C5, CY, and C6. This is my first choice. Okay, macam kamu dari bilik kamu nak pergi ke bilik tutorial. Okay, kamu jalan jauh melalui pejabat, melalui library, and then baru ke bilik tutorial. Or there's another choice where you can choose. You travel straight away from, okay, from A to B through C7 melalui dataran terus. Kamu tak payah pusing-pusing. Kamu terus melalui dataran. Straight away you arrive at tutorial. So that is the meanings. You try to identify how many paths can be taken to travel from the original position to final destination from A to B. So in my diagram right here, I have two choices again. One is through C5, CY, and C6. Another one is through C7. So basically, you just repeat the same thing. You look at the diagram. If you choose the blue color path, you have more than one capacitor. And you cannot do anything if you have more than one capacitor. So what are you going to do? You simplified it. So 5, Y, and 6, obviously they are being arranged in series. So you use series equations to solve it. And now I call it CZ. Because this is still not final step. So I give it the name, I give it the name called CZ. So CZ now, okay, after I simplified it, I remove 5, Y, and 6. I replace with CZ in the next step. Okay, and again, I am having the same two junctions. I'm still going to look at the two junction. Okay, so I'm done with the blue color path. Blue color path right now, I have only one capacitor. And this red color path, I have one capacitor as well. So I don't need to do anything in along the red color path. Okay, so blue color path and red color path, now I have only one capacitor in each path. So done. What am I going to do next? I'm just going to combine two paths together. So in order to combine two paths together, you look at the relationship. Both legs from CZ, they are being connected to both legs from C7. So now you can close the circuit by combining them, okay, by using parallel equations. So parallel equations, now I can call this C equivalent because this is the last two capacitor that I have in my circuit. After combining it, I'm just going to have one left. So this one, I can call it C equivalent now, or C effective. So CEQ is equal to CZ plus C7. And that marks the end of this question. So you plug in the value, eventually you will obtain C equivalent equals to 1.67 microfarad. So now I label it as C effective. Okay, I label it as a C effective or C equivalent. So that is the example, and that is the things that we are going to do today. Okay, our example 1 and example 2 basically is this one. Okay, this type of questions. So now it's 2:26. I give you 4 minutes to write down this example. Okay, to record it, write it down in your own words. Try to do some remarks. See where is the important things, the important notes that you have to know. Okay, saya bagi Anda sampai jam 2:30 untuk buat catatan. Sebab soalan ini dia tak ada dalam buku Anda. Ini soalan tambahan, kamu sendiri tengok. So, buat sikit catatan, and then tengok macam mana nak solve dia.
Madam. Oh,
Yes.
madam. Maximum macam dia punya path tu, in question
Mm-hmm.
dia maximum like 2 or 3 ke dia boleh lebih lagi?
Dalam syllabus Anda, setakat yang saya tengok macam maksimum 3 sahaja.
3 saja banyaknya.
Paling banyak yang saya nampak dalam syllabus Anda, dia adalah soalan jenis begini. Terminal dia di sini, di 2N, and then tengah-tengah, okay, sini ada capacitor, sini sambung lagi dengan capacitor, and then sini sambung lagi dengan capacitor. Contohlah begini. So this is the example. So questions like this, you have 3 paths. Path 1, path 2, and then you have a path 3 right here. So this is the example of 3 paths. And I think this is the maximum number of paths that I've seen in your question, if I'm not mistaken. So this is a terminal. Okay, this is a terminal. So you need to start to solve from the most complicated path in between terminal. Okay, so now let us move on to the next part. Okay, there are some things that I want you to write down again after this, which is related to the energy store in capacitor. So energy stored in capacitor, a charged capacitor stores electrical energy in electric field. That's what I told you before. So the energy stored in the capacitor will be equal to the work done to charge it. So the capacitor does not become charged instantly. It takes time. That's why we have the exponential graph. And initially, when the capacitor is uncharged, it requires no work to move the first charge. So just like you have an empty room, you just throw a charge and straight away it will enter the plate. The second charge requires a bit of work because now it experiences repulsive force from the negative plate. So that is the meanings of this bullet point number 4. So when some charge is on each plate, it requires works to add more charge of the same sign because of the repulsions. Okay, so that's what I explained just now. So blah, blah, blah. This derivation is not that important. What I want you to see is these 2 graphs. Okay, the 2 graphs right here. Graphically, energy store can be calculated from area under VQ graph. Okay, why area under VQ graph? You look at the equation. U equals to 1 over 2 QV. Okay, so obviously now if you look at what happens in a capacitor, when you have a V against Q, actually you have a triangle's area right here, which is equals to 1 over 2 QV. So energy store can be calculated from area under VQ graph. So U is equal to half QV, and the gradient, it represents your capacitance. Okay, because we have C equals to Q over V. Okay, Q, yeah. All right, VQ graph or QV graph. Okay, it's fine. So C equals to Q over V. So from the gradient, you can actually determine the capacitance by using 1 over C. So now, if you look at this diagram, area under this graph, it gives you work done or the energy. But if you look at, okay, this is capacitor, but if you look at the energy produced by a cell, the energy produced by a cell, the relationship between V and Q is now you have a horizontal line. Okay, you have a rectangle right here. Compared to just now, it's just a triangle. All right. So the relationship between these 2 diagrams, it means that now the energy produced by a cell is more than the energy stored by a capacitor. So where does all the other energy gone? It's become energy loss. Okay, why energy loss? Well, like I told you just now, if you have capacitor and you're charging capacitor, for example, okay, so let's say this is positive plate, this is negative plate with negative charge, positive plate with positive charge. In order to add more electron into the plate, you need to do some work. So the works here, okay, the works to add negative charge into the plate is the energy loss, because you need to waste some of the energy to push, okay, to push this electron into the negative plate. So basically, the energy produced by the cell, it does not equal to the energy being stored in the capacitor. Okay, it experiences energy loss. And that is also why when you charge a power bank, okay, power bank, we have a capacitor in there. So when you charge a power bank, you can feel that it's very hot. Okay, because you store the energy in a power bank, in the electric field between the plate, in the capacitor inside power bank. Okay, but some of the energy becomes heat energy, okay, becomes energy loss, because energy is needed to add charge into the electric field, to add charge into the plate. All right. So if you look at the energy produced by a cell, if you plot it, you transfer it into a graph, you are going to get a horizontal line. Why horizontal line? Because when you look at battery, it comes with a constant voltage. Okay, for example, if you are using a 6-volt voltage, 6-volt battery, then it will keep supplying 6-volt potential difference. Okay, and the amount of charge keep increasing as you withdraw it, as you switch on the battery. So constant V with increasing Q, that is the energy produced by a cell. So if you look at these two diagrams, okay, you can calculate energy loss by using energy produced by a cell minus energy stored in the capacitor. And of course, if you look at the equation, okay, if you look at the equation, this one is U equals to 1 over 2 QV. This one is U equals to QV, meaning that their relationship is half, okay? Half of the energy produced by cell is being stored in the capacitor, but half of the energy become energy loss. So you're actually wasting quite a lot of energy, okay, by using the power bank. Kamu cuma store separuh saja energy daripada kamu directly charge kamu punya handphone contohnya. Okay, so separuh punya energy hilang. So this is the graph that I want you to sketch it. Okay, you write down the equations, you write down the diagram, and then you write down the equation. Right? Why is it important? Oops, why I want you to write it down? Why is it important? Because this is actually one of the past year question. Okay, past year questions minta Anda kira energy loss. Dan masa itu ramai pelajar dia tak reti kira, sebab apa? Sebab ini actually dia tak ada dalam syllabus Anda. Dia kena guna sikit pemahaman Anda sendiri. By looking at the equation U equals to 1 over 2 QV, by looking at the equations U equals to QV. So pelajar sendiri sebenarnya kena fikir higher order thinking sikit, hot sikit, baru boleh jawab. But now I make it easier for you. I give you this diagram. I want you to write it down. Okay, I explain this diagram to you. I want you to write it down. So again, I give you until 2:40 to write it down. Okay, lukis gambar raja ini, label semua, lukis tulis equation supaya Anda nampak. Alright, and you have energy loss. Why? Because energy is needed to add negative charge into negative plate. Okay. So now let's look at next one. Okay, so this example, I will just skip it. Basically, it just asks you to calculate energy supply, energy stored, and energy dissipated as heat. Now, charging and discharging capacitor. So a time constant, now time constant is just a mathematical equation. It tells you the relationship between the tau RC and it is the relaxation time. Okay, it tells you how quickly the capacitor charge and discharge. That's it, okay? But that is not the definition. The definition depends on the whether you're looking at charging or discharging process. So the time constant for a circuit used to charge a capacitor is defined as the time required for the capacitor charge or the voltage to reach 63% or 0.63 of its maximum value. How to obtain this value? How to obtain 63%? Actually, if you look at the equations for Q, Q equals to Q naught bracket 1 minus exponential negative T over RC. So we substitute T with RC and then we simplified it. Eventually, we will find that Q final is equals to 0.63 Q naught. So that is our reference point, okay? Tau equals to RC actually is the reference position. Why? Because like I told you before, it's going to take forever to fully charge or fully discharge a capacitor. Therefore, in that case, okay, the scientists, they all need a reference time for us to identify how quickly the capacitor can charge or discharge. Because you cannot take the time to fully charge, you cannot take the time to fully discharge. It is impossible in reality. Okay, it is impossible in reality. Therefore, they need a new reference line and they choose tau equals to RC as a reference point. All right. And then when it comes to discharging process, we have Q equals to Q naught exponential negative T over RC. And when in a discharging process, time constant is defined as time taken for the charge to decrease to, okay, just now is to increase to reach. Now is to decrease to 0.37 or 37%. So again, how to obtain this value? You obtain this value by substituting T equals to RC into the equation. So RC over RC is equals to 1, exponential negative 1 give you 0.37. Just now, I give you 0.37 as well, but then because you have a 1 right here, so 1 minus this part, 0.37, you obtain 0.63. So that is the charging and discharging process, and that is how we obtain the 63 and 37%. So I give you 2 minutes to write it down. Okay, you just write down in your books, take a bit of note how to obtain this value. Because once again, this is one of the past year question. Ask you to prove why 63% of maximum value, why is it 37% of its initial value? So you yourself have to know how to prove it. Okay, so I give you 2 minutes to write it out before I proceed to the next section. So now let's see. Okay, so charging, discharging process, I already explained it in a previous class. Right? Yeah, Anis, kenapa? Tertekan.
Tertekan.
Okay. So charging, discharging, I already explained it before. Okay, I already explained it why you got all these shapes. Okay, so yeah, we can just skip it. Just that when it comes to a charging process, I think this one, the two equation is not given in your books. Maybe you can write it down. So I naught is equals to V naught over R. Okay, I naught, therefore you use V naught. So V naught, you can replace it by Q naught over C. Therefore, I naught can also be calculated by using Q naught over RC. Okay, Q naught over RC. Right, sebab V naught equals to Q naught over C. All right, so from here, you can actually obtain I naught. You can actually calculate current by using Q over RC. Okay, so ini sikit sahaja kamu catat. Next. Capacitor with dielectric. Okay, so dielectric, I already explained it to you. So the things that I want to go through again is just the four equations right here. So dielectric constant, also known as relative permittivity. It is defined as the ratio. So meaning that epsilon R, okay, this is an epsilon R. Epsilon R is a dimensionless quantity. Therefore, if you look at, okay, if you look at the next statement, it tells you dielectric constant is a dimensionless constant, or it has no unit. And since it increases the capacitance by a factor of epsilon R, okay, we can also write it as epsilon R equals to C over C naught. Now, how to obtain these equations? Basically, okay, you just use this. C equals to epsilon A over D, and also C equals to C naught equals to epsilon naught A over D. Right? So you arrange the equations, you plug it into the first equations, then you obtain the second equation. So from second equation, okay, we use relationship C equals to Q over V, and then C equals to, okay, C naught equals to Q over V naught. You replace these two equations into the equation number 2, then you obtain equations number 3. Now, in order to obtain equations number 3, there is a condition. Okay, the condition is that we assume, okay, assume Q is constant. So how to assume Q is constant? By, okay, by disconnected from, okay, disconnect the battery. Okay, you disconnect the battery. So no battery, no supplier. Okay, no supplier means no additional charge can be supplied to the circuit. So it doesn't matter what you do to the circuit, what you do in a circuit, how you modified it, there will be no additional charge, extra charge flowing in the circuit. Okay, so Q remain constant if you remove the battery, if you disconnect the battery. So if you arrive at step number 3, you can then calculate, you can then derive one more equations by using V naught equals to E naught D, and then V equals to ED. All right, D is a constant value. Why? Because you didn't change the distance of the plate. Distance is constant, regardless of whether you insert dielectric or not. All right. Some students, they have misconception. They thought that by inserting dielectric, then they will have a smaller D. No. Okay. Distance between two plates is fixed, unless the question tells you you change the value. Otherwise, it's constant. Inserting dielectric or not, it won't affect your D. Okay, so by using V equals to ED, then you arrive at equations number 4, meaning that epsilon R, the dielectric constant, can be calculated by using 4 different equations. Depends on the information given in the question. Okay, so you have epsilon R equals to epsilon naught equals to C over C naught equals to V naught over V equals to E naught over E. The one with a 0 subscript means that is the initial, or that is the value in air without dielectric. So in order to obtain these 4 equations, we assume battery disconnected. Okay, so when battery disconnected, Q remain constant. Okay, Q remain constant. What if what if battery is connected? All right. Okay, so the process here, I'm not going to explain it anymore. I discussed it before. Now let's see, what if battery is connected? If battery is connected, means that there is a still supplier in the circuit. So it means the numbers of Q is no longer constant. And since capacitance must be increased when dielectric is inserted, so C equals to epsilon R C naught, because from these equations, we know that final C, the C with dielectric, must be greater than C. So if V is constant, now how do I know V is constant? If you have a circuit, this is capacitor, oops, okay, capacitor, and then this is the power supply. Now you still connect it to the battery. When you insert dielectric, okay, when you insert dielectric in between the capacitor, inside the capacitor, C increased, okay, C increased. So C equals to Q over V. Now I want to charge it again until it is fully charged. When it is fully charged, VC again is go back to V electric, okay, your V supply. So therefore, we can assume the V across capacitor is constant. Why? Even though the moment you insert dielectric, the V drops, but then because it's being connected to the battery, it will keep charging the capacitor until it is fully charged again. And when it's fully charged, well, we can then assume the V is constant. Okay, now when the V is constant, meaning that by looking at this equation, C is directly proportional to Q now. So this is the only time where C depends on Q or C depends on V. Okay, is when you are playing with a dielectric. Means that you are changing the physical structure of the capacitor. Otherwise, okay, otherwise your Q and V, it won't affect your C. All right, and C has nothing to do with Q or V. If you are keeping the same physical structure, if you are not modifying the capacitor. All right. So in this case, if V is constant, then how are we going to derive the equations? Now we're still going to use C naught equals to Q over V, but now it's Q naught over V, okay? Where it shows us that Q is related to C right now, it's proportional to C right now, where my V is constant, if it is being connected to the battery. And then C is equals to Q over V. So plug it into the equation, you get a new equation called Q is equals to epsilon R Q naught. Okay, or if you rearrange the equations, basically it is epsilon R equals to Q over Q naught. So that is another equation for you to calculate the dielectric constant, provided if battery is connected and our V remain constant when you insert the dielectric. Okay, when you insert the dielectric. Kalau tidak, then you cannot use this equation. Okay, if you're not inserting dielectric, if battery is not connected, then you cannot use this equation. All right. So this is the last part of chapter 2 that I want you to write it down. So you write it down. We will start to discuss example 1, 2, 3 at 3 p.m. Okay, so kamu catat and then take a short break. We'll continue again at 3 p.m.
Madam termute.
Saya termute, thank you. Okay, now let's look at the example 1. So example 1 figure shows a circuit with 5 capacitors. Calculate the values of effective capacitance between terminals A and B. So what I want you to do right now, you look at the diagram. You are given A and B, A and B. A and B is the terminals, then it means they are being connected to the power supply. Okay, so actually here they have a hidden battery here. Okay, actually it's a hidden power supply, but question just ignore it. Okay, it's not ignore it. They didn't show you. Okay, maybe they got some more complicated terminals circuit on the other side, so it ends at A and B. Okay, but anyway, what we want to do right now, okay, we want to simplify the circuit. Okay, and we assume A and B is a power supply, it's a terminal. So I want you to use 5 minutes to try to solve questions A. See whether you can get the right answer or not. Okay, kamu guna 5 minit, saya nak anda cuba. Tengok anda boleh dapat jawapan tak. Alright, kalau boleh dapat jawapan, bermaksud anda faham. Kalau tak boleh dapat jawapan, nanti bila saya bincang, kamu tanda dan tengok manakah kesilapan anda. Bahagian manakah sebenarnya yang anda masih tak faham. Alright, so 5 minutes for you to solve it. Okay, questions A. So if you are done, if you want to try questions B, go ahead. Questions B is 2.0 microfarad. So 5 minit, sepatutnya boleh siap. Dalam exam, kalau kamu guna lebih daripada 5 minit, itu dah kira agak lambat dah. Alright, so 5 minutes for you to try questions A. Okay, so let's see whether you can get the answer or not. Wait, yeah. Okay, now let's look at questions A. So how are we going to solve questions A? Okay, it's very simple. Now you look at terminals. Terminal AB is located on the left-hand side. Okay, so we're going to start from the capacitor. Yeah. So we're going to start from the capacitor that is furthest away from terminals AB. Okay, so which means we're going to start from this 3 microfarad capacitor. Okay, this 3 microfarad capacitor. So before I start, I would like to label the diagram first. So C1, C2, C3, C4, C5. Okay, C1, C2, C3, C4, C5. I'll label it first. So questions A, how am I going to solve it? So if I start from 3 microfarad, okay, first I need to know where is my junction. So the junction that is closest to 3 microfarad is right here. Okay, the T junctions, right? The junction is here, the orange color point. So from junctions to junctions, now I see, okay, how many capacitor do I have from junctions to junctions? So this is the first path to travel from junctions to junctions. Okay, kamu tengok, kalau kamu nak travel dari satu junctions ke satu junctions lagi, di dalam laluan itu dia ada berapa capacitor? So from junctions to junctions, I have 2 capacitor right here. Okay, and these 2 capacitor, obviously they are being connected in series. So I'm going to label it as CX. Okay, so I have 1 over CX equals to 1 over C2 plus 1 over C1. Okay, 1 over C2 plus 1 over C1. So they are being connected in series. So if I simplified it, I have a 1 over Cx equals to 1 over 2 microfarad plus 1 over 3 microfarad. Okay, so Cx, if I got it right, I should obtain 6 over 5 microfarad. Okay, I should obtain 6 over 5 microfarad if I got it right. Done. That is the first step. Okay, first step, if you look at the capacitor in between these 2 junctions. Next, okay, I have a second choice to travel from junctions to junction. First one is through the external path. The second one is a shortcut. So the shortcut, okay, if I travel from junctions to junction, the blue color path, I have only 1 capacitor. So which means I'm just going to add them up. So just now I already simplified C1 and C2 into CX. Therefore, the second thing that I'm going to do, I'm going to call it CY. So CY equals to CX plus C3, which is equals to 11 over 5 microfarad. Okay, 11 over 5 microfarad. So that is the first path. Okay, I already simplified C1, C2, C3 into CY. I already combined these 3 capacitor into CY. So next, I'm going to see, okay, I'm going to redraw it so that you can have a better idea on what is going on. All right, so now I am left with C4 and C5. This is my terminal A. This is my terminal B. And then here is a 3 microfarad. And then here is my CY, which is equals to 11 over 5 microfarad. And then right here, I have 4 microfarad. Okay, 4 microfarad. So next thing, now I cannot look at the orange junctions anymore. So straight away, I'm going to proceed to the terminal. Okay, I will just proceed to the terminal. So terminal right here would be my next junction. The next point, next 2 points that I'm going to use as my reference position. So from junctions to junctions, okay, from junctions to junctions, now it covers all 3 remaining resistors, which means now these 3 capacitor my C4, C5, and CY, all three of them, they are being connected in series. Okay, so okay, because now, okay, the three remaining one, I'm going to combine all of them at once. So this one is my C equivalent. So C equivalent is equals to, okay, 1 over C equivalent because series, 1 over CY plus 1 over C4 plus 1 over C5. Rearrange the equations. CEQ is equals to 0.96 microfarad. Done. That is the answer. And that is how you solve it. Okay, that is how you solve it. So I give you 1 minute to write it down. Then I will go through questions B quickly with you guys. Okay, 1 minit lah bagi anda catat sebab dia senang saja. So if you got it wrong, you try to mark your own answer. See where is the mistake. Okay, why did you make a mistake in your calculations? Kamu cuba catat, cuba cari. Di manakah anda buat kesilapan? All right, now let's look at questions B. Okay, questions B, if you understand this one, then questions B, you should be able to solve it very fast because it's very similar. So questions B, now I have terminal A and B once again on the left-hand side. So the one that is furthest away from terminal A and B is this 12 microfarad capacitor. Well, as usual, I like to label my diagram. So C1, C2, C3, C4, C5, C6. Okay, I like to label it. So what I'm going to do again, I'm going to write down, I'm going to identify the terminal. Okay, I'm going to identify the terminal. So the terminals, the junctions, not terminals, sorry, the junctions, the closest junctions to C1 is these two orange color dot. Okay, these two orange color dots. So from junctions to junctions, again, this orange color path, if I want to travel from junctions to the other junctions, from one point to the other point, it's going to pass us through three capacitors. And judging from the way you connect it, okay, the way they are being connected, apparently these three capacitors, they are being connected in series. So now I'm going to call it CA, okay, for these three, the three orange color, three capacitor that's lying on the orange color line. So 1 over CA is equals to 1 over C1 plus 1 over C2 plus 1 over C3. So my CA is equals to 4 microfarad. Okay, 4 microfarad. And then I'm going to see, is there any other alternative path that I can use to travel from one junction to the other junctions or not? And yes, obviously there is, which is this one, the blue color line. So if you look at this blue color line, you have only one capacitor in between these two junctions along the line, so you don't have to simplify it. But if you look at them, blue color and orange color line, they are being connected to the same junction. So which means they are being connected in parallel. Okay, so therefore I'm going to use CB equals to CA plus C4. I'm going to simplify it. Okay, I'm going to combine the orange color and the blue color path together. And now I know that they are being connected in parallel, so I just add them up. So CB is now equals to 8 microfarad. Okay, 8 microfarad. So after I combine the orange color path and the blue color path, okay, the remaining diagram would be like this. Terminals, here is my C5, which is equals to 5 microfarad. And then here is my CB, which is 8 microfarad. And then here is my C6, which is a 6 microfarad, right? So again, it looks very familiar to the previous questions. All right, now you have these three paths, these three capacitors. They are obviously being connected in series. Okay, so next junctions will be the terminal straight away. So three of them, they are being connected in series. Therefore, 1 over C equivalent or C effective equals to 1 over C5 plus 1 over C6 plus 1 over CB. So C equivalent is now equals to 2.0 microfarad. So that is how you solve it. Okay, that is how you solve it. So now let us look at questions 2. In the figure above, C1 is equals to 100 microfarad, and then C2 is equals to 200 microfarad, and C3 is equals to 300 microfarad. The applied potential difference between point A and B is 8 volt. So now what you have, you're given terminal A and B, and their potential difference is equals to 8 volt. And this 8 volt actually represents the V total in your circuit. Okay, it represents the V total in your circuit. So question asks you to calculate the charge on each capacitor. Now, usually when it comes to this type of questions, where it asks you to calculate charge on each capacitor, the potential difference in each capacitor, what I would recommend you to do, okay, you solve the questions, identify the Q and V in every single component first, regardless of whether the question is asking for it or not. All right, because if you do it according to what is being asked by questions, then sometimes you might get stuck. You don't know how to solve the questions. So it will be better idea if you find Q and V in every single component following a given recipe. Aha, now I give you the recipe. All right, I'll give you the recipe. You follow the recipe, you will be able to identify every information in every capacitor. But if you just want to answer the question, sometimes you got lost. You don't know how to solve it. Okay, what can you do to solve the questions? You don't know because you got some missing information and you don't know how to find those missing info. Okay, so my suggestions, my advice is you follow the recipe, you identify the Q and V in every single component, even though question might not ask for it, because it will help you to identify all the other information that is being asked by the questions. All right, now let's look at a diagram. So you have C1, C2, C3. Okay, now you don't know which one is located furthest away from terminal AB because they looks like they're all located at the same distance from AB. Then you start from the most complicated part. So the most complicated part would be C1 and C2. Okay, this looks very complicated. All right, so we're going to start off from here. We're going to start to simplify C1 and C2. So if you look at C1 and C2, how to simplify it? Now you look at C1. One leg of C1, okay, is touching the joint here. Another leg of C1 is touching the joint at point D. You look at C2. Again, C2, okay, both legs from C2 is touching the both terminal, both junction that is same as a C1. So means both legs from C2 are being connected to both legs from C1. In this case, we say C1 and C2, they are parallel. Okay, C1 and C2, they are parallel. So now I'm going to simplify it, but how to simplify it? So parallel, well, again, I'm going to call it a CX. So CX, okay, 1 over CX is equals to, parallel. Parallel is not 1 over. CX is equals to C1 plus C2. Okay, CX is equals to C1 plus C2, which is equals to 300 microfarad. So after you simplified it, okay, after you simplified it, we will then proceed to next step. Okay, so this would be the diagram right now. This is A, this is B, okay, and then I have here CX, point D, and then this is C3. Okay, so after I simplify C1 and C2, now I come to this diagram. So from here to here is parallel. CX and C3, okay, now obviously CX and C3, they are being connected in series. And after you combine the two of them, you will be left with just one capacitor. So now I can call it 1 over C effective. Okay, 1 over C effective is equals to 1 over Cx plus 1 over C3. If I got it right, C effective should be equals to 150 microfarad. Okay, so after I combine it, what I'm going to get, I will get a diagram like this. Okay, so this is my A. Yeah, my terminals A. Okay, terminal A, C effective, and then here would be terminal B. All right. So since you are given a capacitance, the first things that you should do, even though it's not being asked by the question, is to calculate the effective capacitance. Why? Because there must be a reasons why the questions give you the capacitance of every single capacitor. So whenever you have a questions like this, you follow the recipe. Okay, kalau kamu diberi nilai untuk setiap capacitor, so kamu ikut recipe ini. Recipe ini memang it always works. Okay, I cannot guarantee that it works 100% all the time, but I would say 90% it works. If you are given capacitance of every single component, then you follow the step like this. Okay, so what should we do next? Now, just now, we try to simplify it from a most complicated circuit. Now, what are we going to do? We are going to reverse the process. Okay, we're going to reverse the process. So let's look at the green color part first, the green color solution. Now, you have C effective equals to 150 microfarad. So what is the other information that we have about this effective capacitance? Well, if it is fully charged, then the V total, okay, the V total would be equals to VAB, which is equals to 8 volt. This is your V total if it is fully charged. All right, so in this case, usually we assume it is fully charged. Unless when you are doing charging, discharging type questions, then you might have a case where the capacitor is not fully charged or fully discharged. But if you're just given a circuit, we assume it is fully charged. So if it is fully charged, then the potential difference across the effective capacitor is 8 volt. So by combining these two pieces of information, okay, by combining these two, you will then be able to identify the total charge in the circuit. Okay, the total charge in the circuit, Q total is now equals to C effective VAB. So Q total, it is equals to 1,200 microcoulomb. So now that you got all of the information for the last diagram, next step, we do a reverse process. We go back to previous question, a previous diagram. From C effective, you go back to the purple color solution. So why do we want to look at the purple color solutions? Now you look at the relationship between Cx and C3. Cx and C3, they are in series. So what do we know about the capacitor that are being connected in series? If they are being connected in series, then Qx would be equals to Q3. Okay, and then they are equal to the effective or equivalent capacitance of the two of them, which in this case is our C effective. So it is equals to Q total. So Qx equals to Q3 equals to Q total. So what does it mean? Now it means now we have all these informations already. We have Cx equals to 300 microfarad. And then we have Qx equals to 1200 microcoulomb. And then we have C3 equals to, well, given 300 microfarad as well. And then Q3, according to our analysis just now, it is also equals to 1200 microcoulomb. So now you have C, you have Q, you have C, you have Q. You can then proceed to determining the V. So Vx is equals to Qx over Cx, which is equal to 4 volt. And then V3 is also equals to Q3 over C3, which is also equals to 4 volt. Does it make sense? Yes. Why? How do I know that they make sense? Because they are being connected in series, and in series, V total is equals to V1 plus V2. So now you look at this one, Vx plus V3 give us VAB, which is the total value. So it makes sense. All right. So in this case, I've done calculating it, I've done checking my answer, and they are all correct. Okay, and they are all correct. So what am I going to do next? I'm not done yet, because question is asking for the charge on each capacitor. What I have right now is just Q3. I don't have Q1, I don't have Q2 yet. I only have Qx. So which means I need to reverse the process for one more time. From the purple color solutions, I'm going to go back to the original diagram. Okay, and in this case, the information that we simplify just now is C1 and C2. So what is the relationship between C1 and C2? C1 and C2, they are in parallel. If they are in parallel, the information that we have right now is the V. V1 is equals to V2, which is equals to, well, if you combine them, they become Vx. So I have Vx equals to 4. Okay, Vx equals to 4 volt. So V1 equals to V2 equals to Vx, which is equals to 4 volt. Well, again, if you look at these solutions once again, now I have C1 equals to 100 microfarad. I have V1 equals to 4 volt. I have C2 equals to 200 microfarad. And I have V2 equals to 4 volt. So I have C1, V1, C2, V2. That means that I can calculate I can calculate Q1 and Q2 now. So Q1 equals to C1, V1, which is equals to, right now I have 400 microcoulomb. And then Q2 equals to C2, V2, which is 800 microcoulomb. Now let's check, see whether it makes sense or not. So when they are in parallel, we know that Q total, okay, Q total should be equals to Q1 plus Q2. So Q1 now I have 400, Q2 I have 800. When I add them up, they are equals to 1,200, which is the amount of Qx. So yes, again, it makes sense, which means now I have the right answer. Okay, my V makes sense, my Q makes sense, everything makes sense. Now it means I got the right answer. So now I can proceed to answering the question. So when it comes to this type of questions, I would suggest you to do the step first, this cycle first, and before you answer it. Okay, so when it comes to the questions, okay, so mungkin sebelum kamu tulis solution A, B, C, kamu buat di tajuk besar dulu, so baru kamu nak jawab kan. So how are you going to answer? So in a A, okay, in a A right here, what you can do, you can say refers to the above, okay, step refer to above. And then you write out the answer, Q1 berapa, and then Q2 berapa, and then Q3 berapa. Okay, so step refers to above, you write out the final answer. Okay, and then your B and C, well, basically you got all the answer already, you see. So B asking for potential difference, A asking for charge, B asking for potential difference. So do you have V? Yes, again, you do have. So again, you say refers to above, okay, step refers to, okay, refers to, maybe to questions A, for example, refers to A. So you write down the answer. V1 is how many? Okay, V2 is how much? And then V3 is how much? All right. And then a potential difference between point A and D. So potential difference between point A and D, you look at these questions. Between A and D means that it's actually asking for the potential difference across these 2 points. Okay, let's look at the original diagram. So it is asking for the potential difference across these 2 points, across C1, C2, okay, across C1, C2. So basically that is your Vx. Okay, so in this case, we have Vx already. So your Vx, okay, so basically you repeat this statement, okay, repeat this statement here. So Vx equals to VAD, which is equals to 4 volt, right? So that is how you calculate it. So now I give you 5 minutes to write down the solution. If there's anything that you don't understand, you may ask. Okay, 5 minit bagi Anda catat. So kalau ada soalan, Anda boleh tanya. Sebelum saya proceed ke soalan D. Alright, kita fokus pada soalan ABC dulu. So 5 minutes from now. Okay, kalau anda dah siap, anda actually boleh cuba example 3 dulu. Okay, example 3, idea dia, konsep dia sama macam example 2. You make a cycle. Okay, you make a cycle. Okay, I hope you understand these questions well. Okay, because this type of question is very common in the exam. So at least you got an idea on how to solve it. You understand the concepts on how to solve this kind of questions. Okay, next, let us look at example 3. Okay, let us look at example 3. So how are we going to solve example 3? Figure shows a combination of 3 capacitors where C1 equals to 100 microfarad, C2 equals to 22 microfarad, and C3 equals to 47 microfarad. So once again, you're given the values of 3 capacitance, meaning that you can use the same techniques to solve this question. All right, you can start from the diagram given, you simplified it, and then you do a reverse process to identify all of the information. So a 20-volt supply is connected to the combination, determining the effective capacitance in the circuit. So now you're given a circuit like this. Okay, so what you have to do now, don't even have to wait for the questions to ask you to calculate effective capacitance. You are given 3 capacitor, meaning that you will need the effective capacitance in the solution. Okay, otherwise the questions won't give you all of them. Okay, if the questions want you to find capacitors, maybe they won't give you all 3 values, maybe they'll just give you 1 or 2. So when you're given all 3 of them, okay, I can say 99% for sure you need to calculate effective capacitance. All right, so what are you going to do? Now you have the questions like this. Well, we are going to simplify it. How to simplify it? Where is the terminal? So the terminal, well, it refers to the battery, which is our 20 volt right here. So this is our terminal. Okay, this is our terminal. So the place that is furthest away from my terminal is a C2 and C3. All right, and let's see whether we should start from C2 or C3 by looking at the junctions. So we have only one junctions right here. Okay, and C2 and C3, they are both being placed along the same path. So you don't have to think whether you should start from C2 or C3 because you need to solve both of them at once, okay, at the same time. So C2 and C3, obviously, they are being placed in series. All right, they are being placed in series. So I'm going to call it again CX. So 1 over Cx is equals to 1 over C2 plus 1 over C3. Okay, and then, well, maybe I can call it like this. I think it will be easier for you. I'm going to call it C23. Because I only have 3 resistors right here. It's unlike examples that I showed you just now where you have 7 capacitor, that it will be hard for you to use this technique. Okay, usually when we have just a 3 or 4 capacitor, we can label it like this. When you want to combine C2 and C3, you label it as C23. So 1 over C23 equals to 1 over C2 plus 1 over C3. Plug in the value and rearrange the equations. You should obtain C23 equal to 15 microfarad. Okay, 15 microfarad. So after you simplify the circuit, you will obtain a diagram that looks like this. Power supply. And then here is your C1. And then here is your C23. Okay, C23. So this is your 20 volt. So C1 and C23. So you're still looking at the same junction. But now what you want to do, you want to combine these 2 paths. Okay, you want to combine these 2 paths right now. So initially, you have 2 capacitors lying on the same path. Therefore, you solve it by using series method. Now you have 2 capacitors along the different path, but they are being joined, they are being connected at the same junction. Meaning that now they are being connected in parallel. And if you combine them together, that will be the last capacitor that you have. Therefore, this one I can call it C effective. So C effective equals to C1 plus C23. So C effective is equal to 115. Okay, 115 microfarad. Okay, 115 microfarad. So if you combine them together, basically this is your final diagram. Okay, so you have a 20 volt right here, and then this is your C effective. Okay, this is your C effective. So if you got it right, your C effective is equals to 115 microfarad. According to the diagram, now because C effective is being connected in parallel with the power supply, therefore if it is fully charged, V total is equals to 20 volt. Okay, V total across the effective capacitor is equals to 20 volt. So by combining these two pieces of information, once again, we should be able to obtain Q total. So Q total equals to C effective V total. All right, so Q total, it is equals to 2300 microcoulomb. Okay, 2300 microcoulomb. So just now we simplify the diagram from the original diagram to the red color diagram, from red color diagram to the blue color diagram. Now we want to reverse the process. So from blue color diagram, we go back to the red color solution. In this red color diagram, the information that we have right now is C1 and C23, they are in parallel. Okay, they are in parallel. So if they are in parallel, means that they have same potential difference. Okay, and if you combine the two of them together, they are known as C effective. So it is equals to VT, which is equals to 20 volt. Okay, which is equals to 20 volt. Now that you have V1 and V23, and you also have C1 and C23. Okay, so C1 equals to 100 microfarad, and V1 equals to 20 volt. C23 equals to the green color solution, 15 microfarad. V23 equals to 20 volt. These are the information that we have. So by using these two informations, V and C, you can then determine the Q. Q1 equals to C1 V1, which is equals to 2000 microcoulomb. Q23 equals to C23 V23, which is then equals to 300 microcoulomb. So these are the information that we have. And now what am I going to do? I'm going to reverse the process for one more time from the red color diagram to the original diagram. Right? So from here to here, now the changes between these two diagrams is C2 and C3. C2 and C3, they are in series. When they are in series, what does it mean? It means Q2 equals to Q3. When you combine these two things together, they becomes Q23, and we do have Q23, which is equals to 300 microcoulomb. Okay, which is equals to 300 microcoulomb. That is the information that we have. Once you have this value, now you can proceed to determine the values of potential difference. How? Well, we have C2 equals to 22 microfarad, Q2 equals to 300 microcoulomb. We have a C3 equals to 47 microfarad, and then we have Q3 equals to 300 microcoulomb. From here, we can then determine the V. Okay, so V2 is equals to Q2 divided by C2, which is equals to 13. Yeah, let me move it a bit. Which is equals to 13.64 volt. Okay, 13.64 volt. And then V3 is equals to Q3 over C3, which is then equals to 6.36 volt. Okay, 6.36 volt. So that is how you determine it. And then you want to check whether you got the right answer or not. Again, you look at what happens when they are in series. If they are in series, V total is equals to V1 plus V2. When you add these two values together, they are equals to 20, which makes sense because my V23 is 20 volt. All right. Also for question just now, if you want to check whether the Q is correct or not, you look at what happens in parallel. So in parallel, QT equals to Q1 plus Q2. So QT 1 plus 2, this is the general equations ya. Yang saya bagi di sini adalah general equations. Dalam kotak punya, it has nothing to do with the questions. I'm just giving you the general relationship. So in parallel, QT should be equals to Q1 plus Q2. Now let's look at my Q1 and Q2. My Q1 is 2000. My Q23 is 300. Altogether 2300. Yes, Q total is 2300. So that is how we solve it, and that is how we check our answer. See whether we got the right answer or not. See whether we have made any careless mistake in our calculations or not. Right? So once again, I give you 5 minutes to write it down. Okay, I give you 5 minutes to write it down before we proceed to the next question. If you have any questions, you may ask. All right. Oh, just now I forgot the one answer, one question, right? Never mind. You complete this one first, and then we'll go back to questions D just now. Okay, you do it first. Okay, you do this one first. Okay, so far, any questions? So I hope you guys can answer the questions. Okay. Yeah. All right. So let us go back to our previous questions. Okay. So previous questions, okay, I left out the questions D right here. So total energy store, when it's asking for total of the whole circuit, that means you're just going to use effective value, okay, the total value. So U total, okay, basically is equals to, well, you try to see which equations you want to use. For this question, I think it would be easier if you use okay, U total is equals to 1/2 CV, okay, because easiest way. So 1/2 C effective VT squared. So you should get 4.8 times 10 to the power of -3 joule. If you got it right. All right, if you got it right. So total means you're going to look at every components in the circuit. Okay, so from there you then identify. Okay, you then identify the energy stored in the circuit. So if you're looking at, if for example, if the question just asks you to calculate the energy stored in capacitor 1, then you use 1/2 C1 V1 squared. If question asking for total, then you use total value, right? So this one, for example, now, okay, this one it asks you to calculate energy stored in capacitor number 3. So meaning that you cannot use the information for a total circuit, okay? So it's up to you which equations you want to use. Just make sure they belongs to the informations that you use in the equations, in the solution, they all belongs to capacitor number 3. So for example, let's say I use Q square over C. So Q 3 square over C3. Okay, if you want to calculate energy stored in capacitor 2, then you use Q2 square over C2. So if you got everything right, then it is 9.58 times 10 to the power of -4 joule. Okay, 9.58 times 10 to the power of -4 joule. So that is how you solve it. All right, that is how you solve it. So today, okay, now it's the 3:55. I think I will stop right here. Okay, so example 4, 5, and 6, I will discuss it on a Friday. Okay, and hopefully I can finish example 7, 8, 9. If not, I might give you a video. Okay, I might give you a video in doing examples 4, 5, 6, 7, 8, 9. Okay, example 7, 8, 9. But anyway, I will try to finish all 6 questions on Friday. So, which means Friday, please enter the class on time. Okay, please enter the class on time. And again, we're still going to do it online. But yeah, let me stop recording first.